Dear colleagues, dear friends, welcome to the optimization seminar. Our today's speaker is Minh from Federation University, Australia. So Minh received his PhD from the University of Toulouse in France, and his supervisor was Dominique Noll, I guess. And then he was postdoc at different continents, at the University of British Columbia in Canada, and then he moved to Australia, and he was at the University of Newcastle, and then at the University of, I guess, with John Borvine, and the University of New South Wales with Goin Lee, and then he moved on a lecturer position. To the University of Australia, the former University of Ballarat. Minh is working on different topics, optimization, commerce analysis. He has some contributions to signal processing, machine learning, control theory. And today he will discuss a method for addressing sum of ratios optimization problems. So Minh, thank you for accepting our invitation. You have 45 minutes for a talk.
Thank you, Radu, for your nice introduction, and thanks all the organizers for organizing this seminar. I think this is my earliest talk ever, right? Because now it's 12:30 in Australia in the next day. So welcome you to the future. Of course, I'm happy to be here to talk about my recent work. Today I'm going to talk about a proximal subgradient methods for solving a class of non-smooth sum of ratio fractional problems. This is based on joint work with Radu and Guin, who are also here. Yeah. My talk include 4 parts. After an introduction, I will present our proximal subgradient methods for solving a class of non-smooth sum of ratio optimization problems, we show that every cluster point of the sequence generated by these methods is a stationary point of the original problem. In the next part, by providing a unified analysis framework of descent methods, we obtain the conversion of the full sequence of these methods under the so-called Kudika-Lozarevic properties. And finally, we will illustrate our methods by a numerical example. Now let's start with sum of ratio problems. In this talk, we consider the non-smooth and non-concave fractional problem of maximizing the sum of function h here and a finite number of ratios fi of xi over gi of xi. So we see here the ratios are separable, and the numerator is non-negative and denominator is strictly positive. This is standard assumption in sum of ratio of optimization problems. And we know that the classical sum of ratio optimization problem have this form: maximum of the sum ratio, but the ratio is non-separable. But we know that this problem can be written as the sum of separable separable ratio with an additional assumption, as additional constraint here, and as a result, we obtain an alternative optimization formulation of the classical sum of ratio problem. And this problem is also a special case of our considered problem P here. Our considered problem here. So we will call this problem as problem P. The sum of ratio optimization problem have arising in many areas, and also in this topic we consider this class of sum of ratio problem P here, because it covers many important non-smooth optimization problem in the literature. For example, the energy efficiency maximization problem is also a special case of problem P. In this problem, actually it's not exactly a problem P, but it can be considered as a special case of P, as we can see in the previous slide here. And in this problem, the decision variable X is the transmit power, and the nominator RI here is the data rate of the user device. The denominator PI is the power consumption to achieve the data rate RI, and the coefficient WI to weight the user device's energy efficiency. The second example is the generalized eigenvalue problems, which just for the most dominant eigenvalues and the corresponding eigenvector. In numerical analysis, we seek an eigenvector with least number of non-zero entry, so that the information can be easily stored and identified. Mathematically, the sparse generalized eigenvalue can be formulated as this form, and in this form, A and B are symmetric matrix. A is positive semi-definite, and B is positive definite. Function phi here is a regularization function which induces sparsity of the solution. Now, before going further, we should note that of course a special case of sum of ratio problem is the single ratio, right? And a classical approach for solving single ratio problems is the Dinkelbach methods and its variants. In each iteration I, this approach finds an optimal solution xn plus 1 of these subproblems. Here we update theta n by f of xn over g of xn. Xn is the solution of the previous subproblem. However, this approach normally requires that f and g are both smooth. F is convex and g is concave. And more importantly, solving subproblem 2 is typically as expensive and difficult as solving the original problem 1 here. In 2017, Radu and Robert proposed to solve subproblem 2 by using two proximal gradient methods. They require that f is a convex function and g is a smooth function with either concave or convex. Recently, together with Radu and Guin, we solved subproblem 2 by some extrapolated proximal subgradient methods, because here we don't require smoothness of f or g. We only require that g is weakly concave. F can be non-convex. Despite this important progress, it is still not clear whether one can develop proximal methods for solving non-smooth sum of ratio problem, such as our problem P, in the light of the work for single ratio cases. This forms the motivation for this talk, and now we will present our proximal subgradient method for solving problem P. In what follow, we will work on these standing assumptions. We assume that S is the constraint set here. S here, the constraint set. We assume that S is closed but not necessarily convex. Minus H is closed and lower semi-continuous. And for xi from 1 to m, fi is non-negative and locally elliptic on an open set containing si, and satisfy this important inequality. Gi is locally elliptic on an open set containing si and satisfy this inequality. So we can think that the rest inequality here is quite complicated, right? But actually, the inequality A1 here holds as soon as the square root of fi is weakly convex, or is also satisfied when si is compact and fi is differentiable with elliptic continuous gradient. The inequality A2 here also holds when gi is differentiable with elliptic continuous gradient. Now we in order to introduce our methods, we remark that actually we have an equivalent non-fictional formulation for problem P here. So we have a non-fictional formulation P1, problem P1 here. P and P1 are equivalent in some sense, and we have this lemma. If X is a global solution of problem P, then so if X bar here is a global solution of problem P, then X bar Y bar is a global solution for P1, where Y bar is defined by this formula. Yeah, we have a closed formula for Y bar, and also we have the reverse is also true. And in which case both problem has the same optimal value. We also have some relationship between the stationary point of both formulation. And from this, we may think that the methods for solving P have some related to the method for solving P1, right? Now, regarding P1, so here is the problem P1, maximizing this function. If we use alternating maximization, then first maximize this function with respect to y or ye, with respect to yi, sorry. Then we see that this function is a concave quadratic function with respect to yi, right? And maximize with respect to yi is easy, right? We can obtain a closed form for yi here. Then we maximize the function h with respect to xi, and we can use this form has also a proximal subgradient methods for this problem. And here we obtain that the next iteration xi, yeah, actually is the proximal operator of some function at this point. Here win is a subgradient of function hi, function hi here. Si is defined by this. Okay. Now if we replace xi, the red one here, by a initial step, then we get our initial proximal subgradient methods for solving problem P. So we replace the xi by zi. Xi here we replace by zi. So yeah, it is an initial step. Actually, this win here is not always a subgradient of HI, but in some cases it is, but it's not always. And so first for yi we have closed form, and then the main step is to find xn xi n plus 1, and it can reduce to computing a proximal operator. Yeah. In some cases we still have closed form. Yeah, but of course it's not always. Here is the first conversion result for our methods. From now on, we suppose that f is bounded from above on S, on the feasibility set, and we also assume that this set is bounded. They are also standard assumption, right? And we get this inequality for our methods. Here, of course, xn is the sequence generated by our methods. For this for this inequality, it is not it does not show that the sequence fxn is decreasing, but we still can have some other corresponding sequence is decreasing. So we still have some form of descent methods. And we also have that the sequence xn is bounded, and the sequence f of xn is convergent. Given that xn is bounded, then we also have that every cluster point of xn is what we call lifted coordinate y stationary point for P, and this one is the definition of coordinate lifted coordinate y stationary point. Like we take the subgradient, which the coordinate y subgradient. So a natural question is when the lifted coordinate y stationary point become a stationary point, right? And we also have some condition for that. So if one of the following, one of the three conditions hold, then every cluster point of the sequence xn is a stationary point of problem P. So here is the definition of stationary point. Yeah, in some literature we also call it the critical point. Yes, I will not going to the details of the condition here because it is quite long. So, okay, so now we see that our assumption satisfies some subsequent conversion. So a natural question is when we have global conversion for of the methods, and in order to obtain the conversion of the full sequence, we need to use a analysis framework of decision methods. As we said, as I said before, our methods is not actually decision methods, but it still have some form of decision methods. In order to do that, we need the notion of Kudika logarithmic properties, or we call it KL property. A function h is said to be to satisfy the KL properties if there is a neighborhood U of x bar and is constant eta and a continuous concave function phi, such that this condition hold, and also this important inequality hold. It's called KL inequality. Here is the distance between 0 and the subdifferential limiting differential of function h, and normally we in application we just consider the distance as the norm of a subgradient. It does. Of course, the distance is the minimal norm, but normally in practice we just choose a we choose a arbitrary subgradient. In the case when function phi here can be chosen as this form, an exponential s, then the KL inequality tree become this inequality, and we say that function has KL property with exponent alpha. If the inequality hold for every x, then we that call it h is KL function, yeah, or KL function with exponent alpha. If we satisfy this property for any x with the same exponent. Some example of KL function. Semi-algebraic function, KL function with some exponents alpha between 0 and 1. Piecewise linear quadratic functions, KL function with exponent 1/2. It means that it has the KL property with the exponent 1/2 at every point. Now, if you have a decision method, then to obtain global conversion, we can use some form proposed by Artus and Eddie Artus and Zegombon, and Schweiter. There are three key components for this. The first one is mean that the sequence h of xn is decreasing, and this one means that we have some error condition. So we have some estimates of the subgradient in h of xn. We can bound it by the distance between xn plus 1 and xn. And the third condition normally satisfied in the usual algorithm. This framework has been generalized by Peter OWOS for like a more general. So here here we have the distance between xn plus 1 and xn, but here we just have some delta n. But of course, delta to get the convergence, delta n actually have some relationship with the distance between xn and xn plus 1. But here we have two variable xn and un, so we have two sequence, and this one normally applies when we have inertial, when we have inertial step. Then, for example, in our case, we have inertial step. Then we should have the second sequence un, and normally un equal xn. So here is we will have xn h of xn plus 1 and xn. But we can propose a more general framework for analyzing the conversion of Descent methods. We propose that there is another sequence Zn in belong to other space, and so we have the sequence xn in H and Zn in K here. So we have some similar condition here, sufficient decrease and relative errors, and the continuities that I said is normally satisfied in the normal methods. The condition on parameter is normally also satisfied, and here's the condition for the distance. This one is similar to the framework of Peter OWOS, but here we don't need to separate into two sequences. So it can be more than two sequences. And in the framework of Peter OWOS, he don't have the rate of conversion. So we still have the relative. Here we have the errors, epsilon here, but we still get the rate of conversion for the abstract conversion. Yes. So if the sequence xn and zn satisfy the condition, then we and the function h is satisfy the function h satisfy the KL property, then we get the conversion of xn, and also if function h satisfy KL property with exponent alpha less than 1/2, then we get linear conversion. So here linear conversion in this sense. Actually, we still have the other conversion rate when alpha is when alpha equals 0, then we have finite conversion, and when alpha is bigger than 1/2, we have sublinear conversion. But I don't show it here. And applies our abstract framework, we obtain global conversion and linear conversion for our proposed methods. So here we need the Fi and Gi are continuously differentiable, and also subgradient of Fi over Gi is Lipschitz. This function we call the merit function for our problem. And if this merit function satisfies KL property, then we get the conversion of Xn regardless of the initial point. Here should be X star, sorry. And if the merit function G here satisfy KL property with exponent alpha less than 1/2, then we get linear conversion. But the question is when we have the second K here, when the merit function satisfy KL property with exponent 1/2. We have some example for that. First is we look at the general line eigenvalue problem with cardinality regularization. So our second motivation here. So here, and we said that the function phi here can be a regularization function, and if we choose phi equal so phi here equals the zero norm of X. So we know that zero norm of X is not the norm. It's a pseudo norm, right? That counts the number of non-zero entry in X. So for this problem, the corresponding merit function G in the previous slide, the function G here is we denote by phi hash. So in this case, phi hash have this form. And we can prove that the merit function satisfy KL property with exponent 1/2, and as a result, our methods apply to this problem admits the linear conversion. Okay, and if we change the regularization by the sparsity constraints. So here is sparsity constraint. Yeah. This can be include to we can write in this form. So here's CR is the constraint set here, part of constraint set, but we include it in here's the indicator function, right? So it all the constraint here is we include here, right? And here the matrix A is positive. Of course, it's symmetric and positive semi-infinite. So in the merit function we have the minus of fx here. That's why we have the a0 equal minus a. So it's minus a is only it's not the positive semi-definite anymore. But it's still symmetric, and we only need the symmetric property for a in this case. And we also get the Kunikalo-Zacevic property with exponent 1/2, and as a result, our methods also linearly converge in this case. Now we arrive at a numerical example to illustrate our method. We consider the sparse generalized eigenvalue problems, as I mentioned before. And in this problem, we consider P observation Z1, Z2 until ZP belong to RD, each of which belong to one of two distinct classes. And we are considering the binary classification problem. Now let's AK is a subset of the set from 1 to P contain the index of the observation in class K with PK equal to the number of element of IK. K here run from 1 to 2. P1 plus P2 equal P, and less mu K hat is the average value of the ZI. Then the so-called within class and between class covariance matrix as given by this formula. Now the classification problem using the Fisher discriminant analysis can be formulated like this. So it's exactly the generalized eigenvalue problem that we mentioned before, right? And we call this problem is SFDA. So SFDA is stand for Fisher discriminant analysis. And here's the function phi here is a regularization problem that induce sparsity. In 2018, Tan and his co-authors proposed truncated regularized flow methods to solve these problems, and their methods proved to have local linear convergence, and in their case, they choose function phi here is indicator function of CR. The CR is defined like this, before. So it means that they are in this case. In this case with sparsity constraint. Our methods work for both sparsity constraint and also cardinality regularization. It means that also work when function phi equal to the L0 norm, and even better, we obtain global linear convergence. So in our simulation, we adopt the same settings as in the work of Tân and the co-authors, and we run their methods and our methods for 50 trials. And here is the comparison between their methods and our methods. We can see that our method is competitive in terms of objective value. Here, look at that. We want to maximize the objective function. It's not minimize. Okay, and we also have a shorter CPU time and also less number of iterations. And it's the pictures. It's this one is decrease the distance between xn and the solution x star in every iteration. Our method in blue, and the methods by Tân and the co-author in red. So in the second case, when we use cardinality regularization, we don't have any other method to compare. So we just show our performance. But you can see that here in terms of the objective value, CPU time, or sparsity level of computed solution, we can see that using cardinality regulation is also good compared to the other methods. I list here some key references, and the talk is based on these two papers. Thank you very much.
Thank you, Minh, for this very interesting talk. Are there any questions? So then let me ask some questions. Minh, so if one would just, okay, first of all, try to consider the same problem, but with respect to some linear constraints, do you see a chance here to combine the proximal subgradient method here with a kind of with the ADMM algorithm or a primal dual algorithm? How would you deal with linear constraints?
You mean when we have linear constraint, right?
Yes.
So I think when we have linear constraints, we should use, yeah, as you said, primal rule or ADMM in the subproblem, because here we open for that. We open for that, right? When you have linear constraint, so it will be included in the subproblem here, right?
Okay, but then you would you would use a Lagrangian type approach.
Yeah.
Okay. So I'm asking this is I have a collaboration with an institute in Vienna. This is an institute for acoustic research. So they have many problems coming from signal processing, but these signals are very specific signals, like acoustic signals, and they have fractional optimization problems within a constraint. So just coming from applications, and they would like to go further step, and then to have a method which they can then apply for their concrete problems.
Okay. Yes, I see. Yeah, but of course, yes, I said that it can be included in solving the subproblem. But I think it's also interesting if we separate in like into more steps. Yeah.
Okay, of course. Yeah. Okay, are there other questions?
I have a small question, if possible.
Sure.
So, yeah, in this one, how do you solve the subproblem xi and plus 1 belong to the argmax? And is it the global solution? Or?
Yes, I said it's only in some special cases we have closed form, and in some hard problem we don't have closed form. Of course, we should use some some existing solver for that. But in our example, in our numerical example, we have closed form.
Yeah, I saw that. But then the next question is whether it's possible the congruence analysis still work if you solve this one like approximately with some small tolerance.
I think it can work in some sense because in our analysis we allow some tolerance, right? Yeah, but but I think it still need some finer for that.
Yeah, so
yeah,
like something
more
like
work for that. Yeah, because we allow some epsilon here, but it's still I agree that it's not straightforward.
Yeah, I see. Yeah, thank you.
Yes,
Thank you.
thank you.
I mean, this is a meaningful question. If one can just separate the function hi from the set S in the algorithm,
Yeah.
in order, okay, by evaluating them in separate ways. But I'm afraid this is not possible, since they are linked to the fact that both the functions fi and hi are supposed to be non-negative or positive on S. Yeah? So this is something which is very specific to fractional programming. Yeah? There is not only an objective function, but also a set S, on which you want this function to be well defined. Yeah? And then it's almost impossible to separate them in the algorithm. So, but then the price to pay is that one has a prox formulation which is not a closed form, which is the argmax or argmin over a given set.
Yeah, right.
This is the yes, but good question. Thank you. Are there other questions? So then I have another question, Minh, just to underline that in the last part, you proved that one can use KL calculus. One can calculate the KL exponent, for very involved problems. I mean, we know there are some papers by Goin and by Tinkhey, where they propose some first models, but now these models can be extended to fractional problems. Now the question is, what is your guess? Can one go beyond this? What kind of models can one consider such that the K exponent can be still calculated?
You mean if we can have some like more rule for the calculate of KL exponent, right?
Yes.
Yes. To be honest, I'm not sure, because we solve case by case.
Yes.
Yeah. I'm not yet see some generalization for that.
Okay. Yes. I mean, probably one can go beyond quadratic, for instance.
Yeah.
In this in these fractional models. And but this is a very, very, very important question. Just to, okay, how far can one extend the KL calculus? Yeah,
Yeah.
such that one can still provide exact KL formulas. Yeah? And
Yeah.
which are very important to guarantee the better convergence, linear convergence.
And also it's also related to your question. It's in the paper of Nguyen and Tinker, they mostly focus on the case of exponent 1/2.
Yes.
Yeah. But for the other case, for example, bigger than 1/2. Yes. How we can have the
yes
calculate for that, and it's also maybe it's also open.
Yes, okay, these are many open questions, but that's a very, very interesting question. Yes, in the exponent of the Kyle function, gives then the nature or establishes the nature of the convergence. Okay, are there other questions? So I have a last question, Minh. So if you go back to the scalarized models, this is the first step. Just we are transforming the fractional problem into a, let's say, a scalarized problem, where they were by using this approach, which was the first time introduced by Dinkelbach and then further extended. So can you please go to one of these scalarized problems?
You mean this one?
Let's take this one and assume that we are in a in a Nonsmooth setting, and if you want in a convex concave setting, can one apply here instead of a proximal gradient the Douglas-Rashford algorithm, even in the non-convex setting? I mean, you are an expert on Douglas-Rashford and this type of methods. What do you think?
I think it's a good idea, but I have not yet tried.
Okay.
Yeah, but it's a good idea.
Okay. So just do something else than the proximal gradient. They just if just try, for instance, Douglas-Rashford or other methods. Okay.
Yeah.
Very good. Even in the non-convex case, yes, it's DOR was studied as a non-convex.
Yeah, but I guess at least you we need to require at least one function is smooth.
Okay. Okay, indeed. Yes. Yes. But still apply the DR method. Yeah, I agree. Okay. So if there are no other questions, then I propose to stop here. Thank you, Minh, for interesting talk.
Yeah. Thank you, Radu. Thank you all.
Yes. Then we will post the video and the slides on our website. The video will be posted also on the YouTube channel of the seminar. I'd like to announce that we will have 2 more talks in this season given by 2 of my co-organizers. So the speaker next week will be Joan Sabach, and 1 week later, Matthias Staudiger will be the speaker, the last speaker of the 4th season of the seminar. So thank you, Minh. Have a good night. See you.
Thank you.